Hello everyone, in this video I'm going to try to explain you how you can build and simulate an MPPT controller, let's say an algorithm where you can extract always the maximum power point of a photovoltaic array. So yeah, I'm going to explain only the perturber observe, which is the most common one, the most common that you will find in any inverter. And later, or maybe in another video, I'm going to try to explain the conductance incremental or inductance incremental, which works with the inductance of the boost converter that we are using here. But first, let's try to understand how the perturb and observe works, because it's also the simplest one. So the first thing you have to do is to get this PV array block. In this case, we are using the Simscape library. So you can see here Simscape. In fact, it's electrical Simscape library. So once you install MATLAB, you should also install this one. Or if you have already installed MATLAB, then you have to download it later in Get Add-ons. I think it's like here. You have to search for Simscape, and you will find like this block. Also, you will find like the RLC branch. This one is also LC branch, although it's just an inductor. Also the diodes and the IGBTs. So yeah, once you have this installed, you have to place a PV array block, which will simulate how the panel works. In this case, these values have been obtained with a random data sheet. Sorry, I think it's from Tensite, the manufacturer, but I'm not sure. Anyway, this panel gives around in standard conditions, laboratory conditions, it gives around 550 watts with these values of voltage and current. We also can work with temperature. We are not working with it, but you can also play with these values. Because this block has here the irradiance input and also the temperature. In this case, we are just going to simulate with a constant temperature, but you can also like build like this some steps to work with different values of temperature and see how the production gets modified. But we are going just to work with different values of irradiance. So we will start using 700 watts sorry per meter squared, and then after some time, like 0.1 seconds, we will zoom 100 watts per meter squared. So we'll have 80 here, 90 here, 1,000, and then we will just decrease these values. So we can see how this model works with different irradiation values and how the system gets adapted. And yeah, you can also see that we have one parallel string and six panels connected in series. So we have six panels with each has 550 watts. So if we multiply this by 6, we will obtain the peak value of the power, which is 3,300 watts. So in standard conditions, the system, after the losses, of course, so it will be like a little bit lower. We would have to get like around this value of 3,000 watts. So after we have modeled this part, you can work with like different parameters of this. It's not like you have to do it same as me. But if you have problems with this, you can also put a comment and I will send you the file. So it's not a problem. But you can work even just with like 3 steps, not like this, and you just have to modify here the time simulation because it ends. Yeah, this is actually it's wrong because these 2 steps like don't work. If you see, the step time is 0.9 seconds and we are just simulating 0.8. But anyway, Okay, so once we have this parameter, this block set, we have to model the boost converter. So in when I did this, I created a subsystem. So if we double click here, you can find this boost converter, which is this one. It consists on more. This is not necessary if you work if you search in the literature the boost converter. Sorry, this branch here does not exist because it's just like filters some noise, like it's a low pass filter, and like the let's say the high frequencies cannot pass like this, and this is works like an also an LC filter. You can add this or not, like as you wish, but of course you need the inductor, you need the transistor, you also need the diode, and you also need this capacitor here. And yeah, you can model this like with your simscape. And we need to control how this IGBT switches with a pvdable m. Sorry, this word really gets stuck. But yeah, you have to get a control, which is this one. I will explain now how this works. So you can also, with the boost controller, what we are doing is to get the maximum power from the system by just controlling the duty cycle of the converter. So if I'm not going to explain how this converter works, like you can search for it. The essence is to have this boost converter to switch or not switch this transistor, this IGBT, to get always the maximum power point depending on of course, the input signals. So here we have the input signals, the current and the voltage that are, sorry, extracted from the PV array. This one. Let's see that you have this M that goes to this subsystem. So if we double click again, you will see this number one, which is this number one. It has two outputs, voltage and current, and of course, if we multiply them, we will obtain the power from the input, from the PV panel. Like we have, for example, 700 watts per meter squared. This, let's say, block gets the voltage and the current of the system and passes to this signal here. So we can actually extract them. And since we have just panels in series, the current will always remain the same, like just if it was one panel, but the voltage will be multiplied by six, so because we have six voltage sources in series, so the voltage just gets multiplied. Okay, so we have this, let's say, two values, and we pass them here, like with labels. From this is a go to, yeah, and this is from. We have these two variables here. We pass them with this zero order hold. That what it does is basically sets when this variable has to get updated, and we need it to be really precise. So we change this to a really low value. It can be zero, but near zero. And we can see I also simulated this already because it takes a little bit time. So to just be faster, I already did it. So as you can see, this is the current, this is the voltage. Sorry, I don't know why this level is wrong, but as you can see, this is a transient episode here that starts at zero, gets around 10 amperes, then gets lower because we have to pass this first transient. And then as the irradiance evolves, the current also adapts to this value. If you can see, like here, that maybe this value matches with the 1000 watts. You can see more or less 13 amperes, with more or less are the this one, the current and maximum power point. This would be the maximum current that our panel can give. Of course, if we have a short circuit, then this current will like increase. But yeah, more or less it matches with this. So this model more or less works. And this is the let's say the most interesting part. It's not the most difficult one to build, which is the algorithm, the perturb and observe algorithm. We have here, I don't know how this block is called. I think it's MATLAB code something. I don't remember now. So what we're doing here is to input. I have to input the current and the voltage, and in the output we have current. Okay, let's say a reference current. It's not our final goal is to get a duty cycle, so this current will just be like a reference to get later this duty cycle. So we have to set a function. In this case is MPPT, maximum power point tracking. We have to input the current and the voltage from the panel without passing any other element later. And we also have to set like some initial values. Okay, these values are not really going to matter, like, because after the first iteration the system will just converge to the values that we need. So this is just to get the first iteration, and then it will get upload here to be the in the next iteration to be the real value that we have now. But I will explain it later, so don't worry. So we set these first values. It can be also zero if you want. Like, I adjusted more or less to the values that we should have with this first irradiance value that is, sorry, 700, but you can set as zero and it should work anyway. We calculate the power in this iteration, like the, let's say, the iteration number one. And we have to set also some limits to this output current that we will have, because as you can see here, if we go back, the maximum current that the panel can give is the short circuit current, that is 13.98. So here we have to get this limit in order to not destabilize the system in case the system decides to convert into a higher value. You have to set this to the maximum short circuit current. The lowest value is 0, and the delta is 0.2. This delta is the increment in each iteration that this current will have in the algorithm. And then we set these two variables, which are the most important ones. This one is to compare the power in the real, let's say, the current power, and the old power, which is the power in the iteration 0, if we are not the current iteration, just the iteration before this one, and also with the voltage. So this is more or less the derivative component. It actually is not, because it's so approximated. It would be like the increment, the gradient of the power and the voltage. So here we have some if and else to decide where the point of working is set in the PV function. If we look at here, we have something like that. If we increment the voltage, the power gets incremented. If we are in the left part of the MPP, the maximum power point. So if the voltage increases and the power increases, we have to keep increasing the voltage to get more power. But once we pass this point, although we keep incrementing the voltage, the power will be lower. If we see, the power is the y axis. So we have to decrease the voltage in order to get back to this maximum power point. So yeah, this is more or less how this works. This also explains, like, if you're working with a high, let's say a bigger step, delta I that I said before, here we will obtain faster this MPP point, this maximum power point, sorry. But we will have like a bigger error, and if we work with a little step, we will like it will take some more time to find this maximum power point, but once we find it, we will work really closer to it. Here maybe we have, I don't know, 500 watts and 800, sorry, 500 watts and 500 watts, because these 2 points are the same, but maybe this point is 800 watts, so we have an error of 300 watts, which we don't want. So yeah, we don't, it doesn't really matter. The step we are using a really low step like this, but I don't know, you can try also other numbers here. You just run the model and see how it works. But yeah, basically it works like that. We have like here the algorithm, we sense the voltage and the current, we see if the power remains the same from the uh, iteration number -1 and the iteration number 0. If the power is the same, that the difference is 0, then we are working on this maximum power point, so we don't have really to get back. But if we have this difference, we have to check if the power has increased or has decreased. In case the power has increased, we have also to see if the voltage increases or decreases, because as I said before, we can like the power can, sorry, the voltage can increase, but the power can decrease if we are working on the right side of the MPP. So this is what does here. We check the power. Okay, the power has increased. The voltage has increased. Yes. So keep increasing, keep scaling this curve. But in case the voltage has decreased, we have to get back. We have to decrease. Sorry, if the voltage has increased, but the power has decreased, we have to get back. We have to lower the voltage level to get back to this MPP. So yeah, if the power has decreased, is like the other way around. Although this matches, because I don't know, if we have decreased the power, if we have gotten back, we have also to check the voltage. If the voltage has decreased, sorry, the voltage has decreased, which is this one, we have to increase. It's the other way around. Okay. So yeah, more or less is what is said here, although we are working with currents. So if the power has if the power has increased and the voltage has also increased, we have to reduce the current in order to get more voltage. Okay, because the power is the product of the voltage by the current. And if not, we set an else and we do the other way around. And also, if the power has decreased but the voltage has increased, we have to do the other way around, just like this with else and if. Okay. And of course, if the power is the same, we set the same current levels. Okay, here we just also can prove that this reference current works between the limits we have set here. And if it really works, then we have to update the new values of pold, and iold with the ones that we are using in this iteration, in the current iteration, and the output is the the reference current. So this reference current, we will call it MPPT. If we check it, we will see that this current, once the irradiance grows, the current does the same, and if the irradiance decreases, the current does the same. So these two variables or features or signals are really correlative. Like they have like one of a correlation matrix value because they're proportional. Okay, so once we have obtained this reference, we have to compare it with the actual current that we are obtaining from the PV saddle, because this will be the error that we have to work with in order to evolve our system. Okay, so imagine if the irradiance increases, so this current increases also, but this this MPPT, that's tracking of the maximum power point, has to get updated. of that, because this current has also to increase in order to get this maximum power point. So we need to treat the error between these two variables. Here with a PI regulator, this is the proportional part, which is set as 1. The integration part, sorry, that has obviously an integrator and also a KI. This is the KP, KI. These two variables, these two parts of the regulator are assumed, and the last thing is to compare with a greater than. This is the relational operator, but it also can be a greater than, I think, greater than or equal is this block here. Let's say, yeah, it's more or less the same. And this is because in the instance where this signal here is above the triangular one, this will be a 1. Wait, sorry. This pulse here will be 1, and once this signal is below the triangular, this will be 0 all the time. Bam, 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 bam. Like this, it's like a repeating sequence. Okay, so with this, we can work with this boost regulation. We obtain this pulse with modulation, and we get this to the IGBT. And this will be all of the controller part. As you can see, we can also check for instance the current in that flows through the inductor. If we check this, we will see that this is like a sheet, but we can see like more or less there's a medium average value. So if we pass this signal through an integrator, we will obtain something like this, which is actually more accurate because we here have this evolution of the irradiation. As you can see, once the irradiation grows, the current does. So yeah, more or less it's the same that we have obtained in the MPPT model. So yeah, once we have done this model, this subsystem, we can finally go to the last part. This part is more optional. I did it because I think that just more to a reality system where we need to set an voltage regulation, let's say like that, because if we are working with a load or with an inverter at 400 volts, it doesn't matter. We have like the maximum power point tracking. If we don't, let's say, process this energy and set this to a reference level so our loads can work with, then the system will be like totally, let's say, worthless, because we cannot apply this system to a nothing. So what we are doing here is to set this voltage output at 400 volts. So the current will be the part of the system that will, let's say, will be modified through the time to give more or less power to the inverter, but the voltage will be always the same. So to achieve that, what we are going to do is, of course, to read with a voltage sensor what we are having in the output of the converter, because these two levels matches with these two ones. So yeah, we are like closing the system. We are just reading here the voltage output. We pass this signal to an integration sorry regulator, and we get the error between the let's say the input signal without any regulator and the output. Why? Because we are going to compare this with the reference voltage at 400 volts. If we see this scope, this is the reference voltage that we desire. Like this will be the perfect solution. Of course, we cannot have this because the system is a dynamic system. It evolves with time. So once this first surge, this first transient episode happens, we have more or less something really, really smooth. Although we have a lot of power, because this part is the part when we have the 1000 watts per meter squared. But if you're working, I don't know, with 80 or 19 watts, it works really smooth. So, and more or less, the system tries to adapt, although even though it's not perfect. So, what we're doing is to evaluate this signal without noise, let's say like that. What we're doing here is to reduce the noise of the signal to be compared with this reference. And we pass this error through a PI regulator again. And in the output, what we are obtaining is the current. If we look at this is the output current that our system will have. Okay, so we have to set this current will be the one needed to have this 400 volts in the output. So through a controlled current source, what we are doing is to all the time set that this current is the one we need to flow in the output, and also will come to here because this is a closed circuit. Of course, the current's flowing from a positive point to a negative one all the time the same. So of course it will also have to be with all the system. But yeah, this is how actually it works with all the parts. We can also, I don't know, play with these different values of temperature, but I don't know, let's check some results. So you can see, for example, this one. This one is the voltage, the current, and the power obtained from the PV array. So yeah, this will be the power. It's among 300 watts that we have said that the maximum power point at 100 watts per meter squared will be higher than this value. So yeah, you can see it works. It's the current that adapts all the time, and the voltage that is always the same in this system. The voltage from the output and from the input is always the same. Okay, the current will be the variable that will be modifying the power all the times. Okay, maybe here it's, yeah, it's more clean. It's the same as I have shown before. Check this one. This one is the, the current in the output. Okay, so as you can see, the first transient episode really is really like high, let's say, because the average value is around 6 and we have almost 14 amperes. So this part can be upgraded, maybe. I don't know how. I didn't study this control part to get rid of the transient episodes, but I don't know. But as you can see, it adapts really well to different values of irradiance, although this part is also like pretty shit. And the voltage, well, more or less is also the same, and this is the current in the inductor. So yeah, it works more or less like the system adapts every time to every instant of irradiance, but of course it can be like updated with more complex techniques that I have not studied, because this is a part of my bachelor's thesis degree, and it's about electrical engineering. It's not about electronics or even telecommunications. With maybe it gets more in detail with the control parts and how to get rid of harmonics and other kind of things. But yeah, it works pretty well. So yeah, this would be all.